to solve for the torsions of prismatic shaft. Okay, so that is a method. And the first method we're seeing is semiminute warping functions. Okay, so this is the second method here. And hopefully we can finish these discussions today. And then Monday, next time, I'm going to introduce the last method, the third one. So for this one, and again, I'm going to write down the whole summaries of the information, and from there I will let you know where this method kick in and to help us the whole solution process. And again, for this topic, and our very fundamental strategy is due to using these assumptions in any cross sections. We assume any point, say x, y, and this is the bar, and this one is on the rigid body rotations. For example, to move to x prime and y prime. Okay, so this is the rigid body rotations on any cross sections. And for a certain shape of the cross section, this point might be floating out or in. That is called warping, right? For circular shaft, and we know the 2 points will stay in plane. Okay, so keep this in mind. And then here, from here, we have a displacement. UV, by definition, is displacement difference between the after and before deform. So that is our starting point. And for example, this rotation angle is called theta. Then that is the beginning of all the story. So UVW, and W is called the warping. And that is the displacement vectors. And from here, from this simple geometry, basically this is U and this is V, okay? So this is U, this is V. We can see is minus Y theta and X theta. And this W usually we assume, and that's going to solve. So that is a function we're simply using the W and function of XY. So that is the starting point here. And with this one, then we are able to calculate strain. And the strain have the non-zero component, basically only have this Z, Zx equal to, so this one is equal to partial W, partial X plus partial partial U, partial Y, right? So this one, partial U, partial Z, sorry. So partial ZX, partial W, partial U, partial Z. Okay, so for this one, and also to proceed this one, then I think I need to have something here. The theta, here is our shaft. I'm going to introduce theta as a function of Z. So here on the top, at the top here, we defined this is from this point move to here. This is due to tension, torsions, and this is our angle of the twist. And our angle of twist corresponding to any cross section here, that corresponding is our rotation theta. So basically, theta is the angle of the twist on the cross sections, and the cross section has the elevation Z compared to the whole length of the shaft is called the L. So usually we have the theta is in linear proportion to the angle of the twist here. So this one divided by L times Z, and this using lowercase here. Okay, so this is the numbers, and this is the assumption we made. Basically, in every cross section, the angle of the twist, and at the level here, we assume that is in linear fashions of the whole things. So that is another assumption we made. Okay, and we define this. Usually, we define this is called the beta. So beta here basically is related to the angle of the twist here. In turn, this number is determined by the magnitude of the torque here. And beta is the number to be determined. So here we can introduce theta as simply equal to minus beta and yz and x and times z beta. Okay, w, x, y. So with the second assumption, we can further introduce the theta, the uv, as a function of z here. So for this case, it's partial w, partial x, and then partial u, partial z equal to minus yz. Minus beta z, minus beta y. Okay, and in a similar way, zy equal to partial w, partial y plus partial v, and partial z. So that is partial w, partial y, and plus beta x. Okay. So to this moment, we have utilized the two assumptions. The first assumption, again, and doing the rigid body rotation in the cross section of the twist of the cross section. The second assumption is define this one. The beta is called the rate of torsion, and we assume that the rate of torsion is uniform, is constant throughout the whole shaft. With this one, then we have the stress, and basically stress component equal to 0, 0, and stress say xz, and 0, 0, and yz, and this is tau zx and tau zy and 0. Okay, basically in magnitude, and we have the tau xz equal to tau zx simply equal to g. And here, if we're assuming isotropic material, so basically this one is partial w, partial x minus beta y, and tau yz equal to tau zx, tau zy equal to g, and partial w, partial y plus. Okay, so we have such things coming up. And for stress, we have the equilibrium of stress component. Okay, here in 3 dimensions, we have 3 stress components, and we can write it down that one. And tau x, partial x plus x, y. Okay, so that is the first equation here. And for the first equation, from here you can see this component equal to 0 here, this component equal to 0 here, and this component tau xz. What is tau xz? Tau xz is the contents here. That is a function, this is a function of xy. This is a function of y only, and taking the derivative respect to z, so the whole terms becomes 0, right? If you look at the contents of tau xz here, tau xz is only the function of xy, so that is partial derivative with respect to z is 0. So the first equation become, we call it automatically satisfied. Good. So that meaning, at least we take the 2 assumptions, so far so good. Okay. So basically here to this point, and that could be the way to verify whether the assumption is appropriate or not. So far so good. Then we proceed the second equation here. Partial tau, and this is yx plus tau yy. Okay, so that's the second equation in a similar way. Tau yx is this term equal to 0. Tau yy is this term, and this term equal to 0. tau yz, again, that you look at this content here, tau yz is a function of the xy only. You look at the details, so basically this term, again, disappear as equal to 0. Okay, so it's good. The third one, for the last term here, this one equal to 0. So last term is trivial. And then for the second two terms, basically that is, that give us something, okay? So basically the second two terms, per our contents, this tau zx is a function of xy, similar function of xy. So the first two terms give a certain function of xy. So that is usually come to the governing equations for something. So the two terms must be equal to 0. And from here, this one gives us a hint to trying to solve for what is beta or what is the omega, what is w there. Okay? And for this one, and we can see. Here, at this moment, it's time for us to introduce the solution strategy. That is the second one, Prandtl stress function. Before we introduce this method, if you would remember what we have done before for St. Venant working functions, this is our first method. Okay, that is in the previous section. If you remember, our strategy there is we have the third warping, the third displacement component is called the warping. We say have this one defined as a beta times certain functions. We simply explicitly let this function has the function of the beta. So in this way, this term will have a beta coming out, this term of beta coming out. Then with the two forms, and defined by that, you introduce to here, that come up with the governing equations for the working function side, right? So that's the strategy. In a similar way, here we come up with something. Something is this. So here is the Prandtl stress function. Okay, so this method is this. Again, they focus on each of the non-zero stress components. They have this function they call the phi xy. Okay, this function is such that for tau zx, that's defined by partial phi, partial y, and tau zy defined by minus partial phi, partial x. Okay. Then we see with this definition of what advantage we have. The advantage is this. With tau x, with the two stress components be defined by this, then you can see these equations become 0. If you simply introduce to the calculation here, so simply this term becomes zx, that is partial square phi, partial x, partial y, okay? And this term becomes partial square phi and partial x, partial y minus you introduce the two terms to here, then you can see this is the same term minus this automatically satisfied. So by assuming this one, then equilibrium equations automatically satisfy this one here. Good. And in this way, we also have derived quantity is this. We simply calculate, so this one, such that in this way the definition is through this and through this, okay? Make automatically satisfy the stress equilibrium equations. Okay, this one here. Good. So that is a note one. The second note is this. We're going to try to come up with the Gamma equation to help us solving for this one. So we play a little bit math here. So the second note is about the mathematical deduction. Deduction, that means from based upon something, you produce something new. That's called deduction. Deduction here we are trying is this. Let me try to determine. Okay, this is the Laplace equation. By definition, is partial square v partial x squared plus this one. And we see what happened about this one here. Okay, so here this one is equal to partial x, and partial v partial x is this one. It's minus tau zy and plus partial y, and this one is the tau zx. Okay. So we want to determine this equation, then we simply have this such a calculation. And then for at this moment, we simply plug in the content of the tau zx, zy there, and do a simple calculation. You should be able to find it. This one is simply equal to minus 2g beta. Oh, that's so nice. So let's come up with the Laplace equation, non-homogeneous Laplace equations, minus 2g beta. G is a material property which is constant. Beta is the what we define in our second assumption, that is rate of the twist, which is also a constant, although at this moment is undetermined yet. But this non-homogeneous term is a constant. Would that be nice? Basically, that indicating we have such equations, and say something like this, equal to a certain constant. Then again, here from solving using differential equation techniques, you may assume that is the certain form, say, do the transformation, we can solve for this one. So for this case, together with certain appropriate boundary conditions, we can solve for this equation, say, in terms of the Fourier series Fourier series expansion or other polynomial based series expansion technique. We can solve for those kind of things. Okay, so far so good. Okay, so here highlight is the Prandtl stress function and how that being compared to our first approach. But again, the two methods, the second method and compared to the first method, they have their own advantage, disadvantage here. We can continue here. So to this moment, this is a Gamma equations. Again, this is, for our case, is minus 2g beta. Okay. And this is a Gamma equations, and now I'm going to focus is on the boundary conditions here. Okay, and then before move on, here I'd like to make a third note. The third note is arbitrary, so it's not that important, but it's worth noting. maybe if you would have chance to read other textbooks, sometimes in certain textbook, this is positive sign. No, it's not negative. Sometimes this is become a positive. Why? That is reason because sometimes people put definition minus sign, rather than put here, they put a minus sign here. Okay, because either way you can see the minus sign go here or go here, it doesn't affect this benchmark of these equilibrium equations, right? So if the minus sign go to here, then this term will have no sign. So just let you know, depends on the people's preference, then you should expecting sometimes it's positive, sometimes negative. But here, just let you know the reasons. And furthermore, even sometimes you will see the people have only -2 here. And the reason because the people, when they define such thing, they scaled by, for example, G beta. They have the terms here, then basically, once they scale down here, the both sides, they have a G beta up here, then they cancel out, only have 2. We good? Okay, just to let you know, it is such kind of the variations of this kind of the form there. Okay. But we stick with our notes, and I adopt this one. So we only stick one form, and then that'll be good. So the remaining is on the boundary conditions. The boundary condition, the same thing as the first approach. So let me write this one very quickly here. The boundary conditions is this. The first boundary condition is among the boundary of cross section. So in any cross section, say, let me pick this cross section here and show that one. So this is XY axis, and then let me just show this segment, okay? So that segment is something here. So this is profile of cross section. Okay. So let me make one. So at this point, so that is a point XY. And here is the tangent. At a point, we make a tangent. Okay. So here that called it tangent has a distance ds, and here it basically is dx and dy. And then on the other side, let me make this is the normal vectors. Okay, and usually we have the normal vectors in terms of the element L and N, right? And in our earlier derivations, we can see the LMM simply can be described by in terms of dx, dy, ds, dy, and that one is probably we can try it with. So basically this is our x-axis, this is our y-axis locally. Okay. So let me call this is called the angle alpha. So alpha plus this equal to 90 degrees, this one plus this one 90 degrees. So alpha is also equal to here, right? Okay. So L, what is L? L is the directional cosine of the n vectors and the x-axis. So basically, this is cosine alpha, right? Okay. Then m is the directional cosine of the n vectors to y-axis. So That means it's cosine. The direction cosine between this vector to y-axis is given by this angle here. And that is alpha plus 90 degrees. Okay? Okay, so this one basically is cosine alpha and minus sine alpha. With this in mind, then we can relate it to the tangential differential. So for this case, you can see from this diagram, you're able to tell basically using this red triangle, can you see the cosine alpha equal to cosine alpha equal to dy ds, right? And sine alpha equal to dx ds. Good. So basically this one equal to dy ds minus dx ds. So that's the reason here in different textbooks, and when they describe the boundary conditions, they have quite a few forms they like. And some people simply using the directional cosine. This is the most primitive, it's from the definitions. And then people like to, in terms of the alpha, and they define the alpha like this one. And some textbooks like to define the vectors in terms of tangential differential, and that is this form here. Good. And I particularly choose the fourth quadrant for display for illustration, because in the fourth quadrant, in terms of tangential, that can give us the positive dx dy. That is the best one I've seen. Otherwise, if we choose the first quadrant, then you can play around. Dx will become point leftward, and that becomes negative. I don't like the negative kind of sign kicking here, so I use this one. I think this is the best one. And again, in certain textbooks, they have such a displacement, such an illustration in using the first quadrant. Okay, you can practice to see how can you work out, but the results should be the same. So that is, right now we spend this one defining the normal vectors. Okay, now I'm going to describe the boundary condition here. For any stress, and here we apply a cos6 formula. And this one indicating is the projection of the stress components into that direction, any directions. And here for n in particular, that is the normal vectors. So that indicating this representing is the projections of the stress component onto the unit out normal vectors of cross section of the boundaries of a cross section. Okay, very long word. Basically, this meaning is we simply project the stress component into this direction. Okay, so that representing basically is a vector form in that direction. So for our case, we only have the torsion applied in the shaft. Do we have any normal loading, like pressure, perpendicular to the surface of the shaft? No, right? We don't have such things. So that means this one should be equal to 0. The 0, that means here from our assignment, we only study the pure torsion. The shaft is only under the torsion. There's no such compressive term or tension term applied to the surface. This one indicating is a component projecting into the normal direction. That means into this direction, normal to the surface. No such external loading. So that is equal to 0. So for this case, then we can derive, and this component, basically tau component, stress component is something like this one here. Okay, so only have the two. So we plug in. So how about let me do this one? 0, 0, and tau x 0. 0, 0, tau yz is symmetric, zx, zy, 0, and then say the n vectors, let me take n equal to L, M, N, okay? So here in general, in 3-dimensional is the 3 components here. But the third one, this one equal to 0. If we take only the third equation, that means tau zx times L plus tau zy times M equal to 0. The first two will become trivial. Okay. Y is trivial, and then modify one term here. Along a cross section here, the n in general, they have the third component in n equal to 0, right? If we only talk about the normal vectors, if you want to be general in 3 dimensions, that should be 0 here. So that making the first two equations trivial. Okay. So now we come to here, and then here we introduce our Prandtl stress function. For the two terms, here let us introduce our specific solution strategy to the boundary condition there. So the two terms will become getting old. So this one is Zx is partial phi partial y plus minus partial phi partial x times n equal to 0. Okay. And then here, if you like, depends on the preference. For example, we can use in this form here. So that means basically partial y. L equal to dy, ds minus, and this is minus dx, ds equal to 0. Okay. So for example, here, and I said that for example is this. Here we have so many forms available to you to pick. And pick one that is the most convenient and most available approach to these solutions. And here, after attempts, you will find this is the best one for current situations. And let me give one more right in here. So from here, you can see this equation simply is a chain rule of d phi ds equal to 0, right? If you apply the chain rule, and to here you can find this one. So here I would say that is equivalent. You good? Okay. So from here you can see this one, what this one meaning. Phi, this is a Prandtl stress function, is a constant. Right? It's not everywhere constant, but it is constant where? This is about the second, this is about this first boundary condition. So tell me, who can tell me this is constant not everywhere, but only specific locations where? You think about this one from the very beginning, this is derived from here, and we talk about this is from here. That is the projection onto the boundary of the cross section. So that means this is constant only valid on where? The boundaries of the cross section. Okay. Good. So such a particular, you're a long way to there, we define the Prandtl stress function like this. And we know we have to solve, we may solve this function by dealing with this stress function, this kind of the differential equations. But however, this boundary condition give us so nice result. We can guess, we might be able to guess appropriate stress, stress function by this one. You good? Okay, so again, this is the advantage of the Prandtl stress function. As long as you can make a good guess or make a good attempt by utilizing these features, then you almost done the whole province. Okay. Before we move on, then let me kick in the second boundary condition here. Let me erase unnecessary information. So erase this one. Okay, so this is stick with the first one. The second one is about the equilibrium, and again, equilibrium of the stress to the applied torque. So this one is the same as we have. So on the top surface of the shaft, okay, so this is the, at this point, we have the tau zy, and we have the tau zx. And around that point, we pick a small element that we call the dA, small area, okay? So upon this one, this stress multiplied with small element, small area, give a small force. Such a small force multiplied with the arm. This arm has the coordinate, has a length x. So tau zy dA, that is small force multiplied with x, that gives us a moment around the origin in counterclockwise direction. Okay, and now for the second, this is the stress multiplied with dA. So tau zx multiplied with dA, that gives us small force. This small force multiplied with arm, this arm has the length y, that gives us the moment at the origin clockwise. So for this case here, we have the given torque, like we're showing here, that is given in the sense of counterclockwise. So let me take the counterclockwise as the positive sign here. So we integrate, and minus, that should be equal to t. So let me rearrange this equation. So that means take the area integral about the cross sections and x, y, z, zy, minus y, zx, and dA equal to t. Okay. So from here we can introduce this term, and in terms of our Prandtl stress function, so let me, this one simply equal to minus partial phi, partial x. This one equal to this one, right? Okay, we introduced this one, so basically that indicating is this a few steps, and here you're going to do the area integral combining with the known given boundaries, and here I skip only two simple steps, okay, to save time. A little bit tired. So here I skip two single lines and refer to the lecture notes. And here we can come up with the whole thing will be simplified as this. This side will be equal to phi dx dy. Okay, and then this one will be equal to actually 2. Okay, so that one will be equal to t. So that is the everything, and we have. So by doing so, this equation will allow us to solve for beta. We know beta, and from here we may guess C, or with the boundary condition one, we may solve for this one. Then everything can be solved directly. Okay, so that is the whole theory of the Prandtl stress functions, and back to the top.